Hey, what's up, guys? My name is Milo McCard. I am an engineer that has worked at Tesla and Rivian, and today I'm going to show you how to do this shear moment diagram with a distributed load on it. To start, we have to do a free body diagram to establish static equilibrium, and so that's roughly to scale. On this left side of the beam, we have a pin-to-pin connection. I'm sorry, we just have a pin connection, and so that means we're going to have a reaction force at A in the Y, and we're going to have a reaction at A in the X. At B, we have a roller connection, and so that means there can only be a reaction at B in the Y. There cannot be one in the X direction. After we do that, we're going to draw in that 15 kips. That's shown at point B. And then we have to figure out what to do with this distributed load right here. Um, because when we're doing our free body diagram, we cannot have a distributed load. We have to treat it as a point load. Uh, and so in order to do that, we have to figure out how much force is actually happening there. And so what we're going to do, we're going to multiply that 2.5 kips by the length that it acts over. And so it's going to be 6 feet. And so if we do kips per foot right here times 6 feet, you can see that the feet cancel and that we're just left with kips. And so this is going to equal 15 kips. And then we have to figure out where do we put this on the actual beam. And the answer is that it just goes at the centroid of the distributed load. And so it's a rectangular distributed load. And so you know the centroid is going to be at half of the length. And so that's going to be 3 feet from the reaction at A. All right, so now we have our free body diagram, but we have 3 unknowns here. Um, the easiest one to do is going to be the sum of the forces in the x, and that's going to enable us to figure out what the reaction at A in the x direction is equal to. And so we set it to 0 because this is statics, and then we say that's equal to RA in the x, but you can see there's no other forces. And so this is true right here. It's just saying that the reaction at A in the x direction is indeed 0. All right, now we have to do the sum of the forces in the y direction. We're going to set it equal to 0 once again because this is statics after all. And then we're going to have any of the forces that are pointing upwards, those are going to be positive forces. And so we're going to assume that the RA in the y is going to be positive. We have minus 15 again, plus RB in the y. And so as you can see, right here, we don't have enough information to solve this single equation, right? If we have 2 unknowns, which we do right there and right there, we need to have 2 equations. And in order to get our second equation, we can generate a sum of the moments. And so to do a sum of the moments equation, we're going to choose point A, and we're going to set that equal to 0, again, because it's statics. And then we're going to take the moment about that point. And so it starts with that 15 kips right here. And you can see that this would cause it to go in that direction. And that means it's going to be clockwise. And so anytime we have a clockwise moment, the standard notation is that it's negative. And so we're going to say negative 15, and then the distance from here to here is 1.5 feet. And then for this one right there, we are going to do the moment as well. And so that's going to be minus 15 again. And if we go back over here, we can see we have 6 plus 3 is going to be 9 feet. And so that's minus 15 times 9. And now the final force that we have is the reaction at B in the Y. And so we are going to do plus the reaction at B in the Y times the distance. And we're doing plus because it's going to cause a counterclockwise rotation, and that's our standard notation when we're doing a sum of the moments. And so now we have to do a little bit of algebra to move this around and to figure out what the reaction is. I'm just going to skip that step and say the reaction at B is equal to minus 15 times 1.5 minus 15 times 9 divided by 15. And if you don't see where that 15 came from to divide by, it's just this guy right there. And this comes out to, let me see my calculator real quick. Actually, I don't need to do my calculator. This all cancels right there, and then we're just left with 1.5 plus 9. I made a mistake actually. So this 1.5 right here should be 3. I don't know why we did that like that. And then these should actually be positive because in algebra we moved them to the other side. So after that mistake, we have that recovery though. This comes out to 12 kips, and it comes out positive because we assumed the correct direction, which is upward. And so now we can take this value and we can plug it back in up here because this is no longer an unknown. And so we're going to do that algebra again. I'm just going to skip some steps. We're going to say RA in the y is equal to 15 plus 15 minus 12, which comes out to 18 kips. And so if we substitute all these back in here, we can just erase that one because it's 0. This one is going to be 18. And then this one right here is going to be 15, just like we solved for. Just like that. And so now I'm going to copy this guy. I'm going to move it downwards. And we're going to start on that shear moment diagram. And so whenever I do a shear moment diagram, I always like to redraw my free body diagram because it makes it much easier when you follow these steps. And so I'm going to draw some dotted lines. And these dotted lines are basically occurring anywhere like there's something interesting happening. In other words, like anywhere there's a discontinuity, when there's like new forces or a change in the forces occurring. And so these ones are easy to see why I would do them here because there's a force right there. But you can see on this section right there, I skipped something. Um, so if you recall from the first step of that free body diagram, we changed this from a distributed load to a point load. And when we're doing our free body diagram, that's fine. But when we go to our shear moment diagram, we have to change it back to a distributed load. And so that's just what I'm doing right here. And good. And so now we're going to have to put another one of those dotted lines in here at the end of this distributed load. All right, so now we have all of those dotted lines in. I'm going to switch back to a solid line, and we're going to start with our shear moment diagram. And so this one's going to be our shear diagram. This is positive shear, negative shear, and then we have 0 right here. And so to start, we have this 18 and it's positive. And so that means I'm going to jump upwards on my shear moment diagram, positive 18 units. And then after that, as we continue moving to the right, we have this distributed load right here, and it's telling us to go downwards. But because this is a constant distributed load, when we go to our shear diagram, it becomes a linear line. And so we know that this entire thing is equal to minus 15 units. And so we know that 18 minus 15 is positive 3. And so this is where we're going to end at positive 3, and then we can just connect those via a line of constant negative slope. And so from here, we're just going to keep going at negative 3 units until we get to this guy, and then we have another downward facing 15. And so we're going to go down another 15 units, and it's going to take us to about 12. And you can see right here, this says 15, it should say 12. And then we're going to carry over all the way to the right-hand side of this. We're still at 12 this whole time. And then right here, we're going to jump up 12 units, just like that. Now I'm going to go ahead and draw the start of our moment diagram. We have positive moment, negative moment, and 0. And the way we get the values for the moment diagram comes from the areas right here. And the way we get that, you can see we have a height of 18 right there, and then this length right here comes from the actual problem. And so you can see it's 6, right? And so this area is going to equal 18 times 6 divided by 2 because it's a triangle, right? Well, actually, that's not it. It's going to be 15 times 6 because we have this area right there that's a rectangle. And then that's going to be divided by 2 plus 3 times 6. And so this comes out to be, let me grab my calculator, comes out to be 63. And then this area right here is going to be 3 times the width, which is also 3, and so it comes out to 9. And then this one should be a little bit easier. It's going to be 12 times 6, which comes out to 72. And so good. Now we can go down to our moment diagram and we can start drawing it. We know that this is positive, and this one's negative. And so at the end of this, at the start of this section, we're going to be at 0. At the end of it, we're going to go up to 63. But we have to figure out, how does this line go? Should it look like that? Should it look like that? Or should it look like that? And the easy way to tell is that right here, there's a really big step. And then as you go to the right, you have a really little step. And so that means the slope on the left side starts out steep and then it gently tapers off just like that. So you can see the slope is steep right there and not steep right there. All right, now we have this center guy right here. It's going to jump up from 63, 9 more units, and we're going to arrive at 72. And we have to figure out what's the line that gets us there. Well, on here, we have a constant line. And so that means on this one, we're going to have a linear line. And then recall for this final section that we had a negative 72, and we have a positive 72 right there. And then we have to figure out, how does this one get all the way down to 0? We have a constant line right here, and so that means on the moment diagram, we're going to have a constant linear slope, just like that. And so that's the shear moment diagram finished.